Okay, we introduced last time the notion of ergodicity, and which was an important concept, meaning in general simply that you have a certain part of phase space where our system moves, and ergodicity means that basically the system, the probability to find the system at some part of this space, of the phase space, is proportional to the volume or to the area of the corresponding phase space. Well, to be very naive example which we started with was that if you have a harmonic oscillator and it moves, of course, if we fix energy of the closed system, then it must the phase space is not anymore 2n dimensional, but it's only 2n minus 1 dimensional. Like here, the particle moves along the circle, and roughly speaking, the average time the oscillator spends in this interval is proportional to the length of this interval. Or in simple words, it's the point representing harmonic oscillator here winds around with a constant angular velocity. And we also generalized this for the case of higher dimensional integrable system, which is somewhat more tricky because we have now 2n dimensional space, and we have not only energy, if we have only energy, so if you restrict your motion by the condition like that, then it's 2n minus 1 dimensional space. And generally speaking, in this 2n minus 1 dimensional space, generic system moves in a very complicated way. But as we will see, it covers more or less with constant density this subspace defined by this equation. But we looked actually at somewhat simpler case, the integrable system. So this is generic system with only energy being conserved. Typically we consider the system with conserved energy. And in completely integrable, I remind you, the situation is this. You have n conserved integrals, so you have the number of constraints is n. Complete integrability means that I probably should use a different letter. It's not yet the action variable. And we assume that the Poisson brackets of these two is 0. And then it's clear that the system moves on n-dimensional space. And moreover, what we said last time was that this space is extremely simple. So in this, the completely integrable system, which are important subclass, but are simple. The generic systems are much more complicated. So the simple n-dimensional space, which we talked about last time, is n-dimensional torus, which is the direct product of n circles. And for generic initial conditions, if the ratio of frequencies is not a rational number, then the trajectory simply covers the surface of the torus with constant density. So the very important, this is some part of classical dynamics, this complete integrability, to which we will return, and we will see how to find the action angle variable. You introduce ik, which are some function of this conserved integral there, but they actually have they are obtained by canonical transformations from these guys, and they form the canonical pairs in the sense of this is a new momentum, this is a new coordinate, and ik phi l. I'm just reminding you what we discussed. Haven't said anything new yet. Okay. Now what else we will need? Yeah, there is a sub-part of classical dynamics which we will not have time to discuss, but which is interesting but not really fundamental, is which occupied many people. It's what happens if you have an integrable system, completely integrable system with small perturbation, how it will move, what will happen to this tori when you add to the Hamiltonian some perturbation which breaks integrability. Actually, it turns out to be a very interesting mathematical problem. It's also a very interesting physical problem because you have when you have a planet moving around the sun, it's a completely integrable system. Why is that, by the way? Do you remember what are integrals which we use when we have just planetary motion?
Angular momentum.
What do you mean by angular momentum? A component or?
So L squared and LZ.
Yes, right. And H, the Hamiltonian itself, they make three conserved integral, and so it's an integrable system. And now you add the influence of other planets, and that's obviously, you don't expect it to be integrable, and it is not. But it is a small perturbation. And this perturbation theory, people developed very sophisticated perturbation theory for such thing. The result, by the way, depends in an interesting way of whether the frequencies are, well, first of all, you assume that the frequencies are irrational, but I mean incommensurate. If you have any two frequencies. But the answer, interestingly, it's a side remark. We will not pursue this direction, but interesting to remember. The result of the perturbation depends on, if it is a rational number, depends on how well irrational number can be approximated by the rationals. Turns out that not all irrational numbers are equal. Some are more equal than the others. So, in the sense that when you try to approximate them by rationals, the error could be different. So you see how subtle it. I just saying it not because we will be discussing this. The whole area is called KAM, Kolmogorov-Arnold-Moser theory. but because just to give you a taste of subtlety of this subject. We will, however, go to something else.
What do you mean by approximating irrational by rational? Because you would expect that you can approximate when you proceed and it's an irrational.
Yeah, well, you have some irrational number n. You approximate it by some rational, and the error is when, let me see what the equality is, m to some power, and for different rational number, these powers are different. Anyway, let me proceed to our main topic, and the main topic is that we will be moving gradually today to continuous mechanics, to hydrodynamics, and so on, and we will talk a little bit about statistical mechanics. Statistical mechanics generally is defined in the following way. You assume first, you are making some assumptions. The first assumption is ergodicity, once again, and if we expect no other integrals but the Hamiltonian, then you would expect that the probability to find the system in some point of the phase space should be proportional to dp dx multiplied by the delta function of h of p and x. So this delta function is what makes, if you apply this rule here, you will obtain a circle. The circle can be, but this is the 2n minus 1 dimensional phase space, and you expect that this ergodicity is fulfilled. This is, however, ergodicity is necessary but not sufficient condition for applying statistical mechanics. We also need something else, namely, we need to assume that when you have a gas and you measure a velocity of some molecule and find it, and then you measure a velocity of some other molecule at some other moment of time, the correlation between these two measurements should disappear very quickly, because there is, if two measurements are separated by the time much larger than the collision time between the molecules, and that should be also taken into account. But then when you have this condition satisfied, you try to describe the system, the probability like that, and that means again the ergodicity simply means that if you have some arbitrary function on the phase space and you have many degrees of freedom and you averaged it in time, you take time to infinity, it should be proportional to the integral when I say proportional, we have to introduce also a normalization. This probability is not normalized. And moreover, the volume of this phase space. So basically it tells you that probability to find P and the system at the point is just the volume of the corresponding domain. The volume of the phase space as a function of energy is simply integral dp dx, the total volume, I mean, P and x. And you have to, this volume, we will evaluate it now for some simple cases. It has a very important physical meaning. Namely, it has all the properties of the entropy. If you take the entropy is defined simply by the logarithm of the volume in which the system moves. And we know that if the system originally, if we have the ensemble of the system occupying certain volume in the phase space, then by the Liouville theorem it is not changing. So there is some trouble here because the entropy is changing. But still, I'm return to this in a moment. But I want first to familiarize you with these things, which you probably know in some form. So let's try to see how all these things behave for a simple gas in a box. And then we will draw some general conclusions. Let's take, let's calculate. Just as with harmonic oscillator, it was very easy to calculate the averages. Here it's also not difficult if the interaction between the molecules is small. The Hamiltonian will be simply the sum and so the volume of the phase space, the total volume. By the way, for those of you who know quantum mechanics, this volume of the phase space is simply the number of states at given energy, number of quantum states at given energy. The notion of entropy has practically the same meaning. Let's calculate first and then think second. So we have volume, which is the delta function. Let's suppose we are in 3D space. So the integral approximate, it's the integral of the number of variables in this multiple integral is around 10 to the 23. But we can, in one line, calculate it nevertheless. So first of all, what will be the contribution of the x part? I start with a simple thing. We have let's first perform d3x integration. What is the answer? And then we will perform the d3p integrations. Yes, just the volume. So more concretely, it's related to the volume of the box, but we have n integration here. So we have it's the let's call it volume, spatial configuration volume to the power of n, integral of the delta function of sum of pi squared to n minus e and now I claim you can immediately figure out how this second integral depends on the total energy. How it depends on the total energy?
So it's a sphere radius root 2m over.
It is indeed the sphere. It's the surface of the sphere. And we can actually very easily evaluate it because when you scale E, pi scales like, I'm not interested in mass, pi scales as e to the 1/2. And so the volume or the entropy as a function of energy is given by volume to the nth power, energy to which power? Almost. That's what will be interesting to us. But don't forget, strictly speaking, there is -1, which is negligible. -1 because the delta function scales like 1 over e. Delta of x scales like 1 over x. So, and some constant which is irrelevant. So we obtained the expression for the entropy, for thermodynamic entropy, which is just, that by the way explains why we'll take the logarithm of the phase volume. It's n logarithm of the usual volume plus 3n divided by 2. 3n divided by 2 by logarithm of the energy. And from here, we can immediately derive the all thermodynamic of the ideal gas, of the gas without interaction. I shall very briefly explain how one proceeds. How one proceeds to the more standard. You can ask, you certainly know the Boltzmann and Gibbs distribution, which are something like e to the minus energy divided by temperature. So where is the temperature here? How it is related? In fact, very simply, it's Boltzmann-Gibbs is simply a convenient trick for the big system to calculate these integrals. I shall explain why. So this integral, I claim, this integral in general is closely related to a different integral where we have not the delta function but the exponential function of this type, and that's much more convenient form. How one is connected to another? To connect them, one uses the following trick. You can always write down the delta function in the following way. You take integral over d beta from minus I infinity to plus I infinity, e to the beta e that's a general representation of the delta function, which is the general formula is that delta function as a function of x is, you can always write it down as dp divided by 2 pi e to the ipx. How to see, that's basically the formula for reversion of Fourier transform. You can derive it in many ways. For instance, how to make sure that this integral is actually, well, let's study the property of this integral. This integral I, change variables in this integral, p plus k, you will get integral dk, dp, e. So we have the identity. Again, it's a digression, I assume you know this thing. You see, we get this relation by changing variables. Since we get this relation, if I is non-zero, only if x is equal to 0. Then you have, of course, to check that when you integrate it with some, if you multiply it by some function and integrate over x, then you get you get the relation, the basic relation of the delta function. You can also regulate, this is strictly speaking not a very, this integral is slightly, it's not convergent in the usual sense. You can always, again, it's just a side remarks, if you know it, that's fine, but we will need these technical details. You can always write it down as e to the minus epsilon p square, when now it will be perfectly convergent in all senses. And then you have to integrate a smooth function, take epsilon to 0, and you will obtain this relation. So if you are, I will not spend any more time for this. If you want to know more, I will be glad to explain it after the class. Anyway, you see that what's happening here is that the e to the entropy is equal to the integral over d beta. And here we have e minus beta h of p and q, p and x, dp dx. I hope it's clear that when I don't write these indices, I mean them. There are three n coordinates here, 3n here. So if we now call, let's introduce the function of beta, which is integral e to the minus beta h dp dx. And then we get the following relation for the entropy, that e to the s is an integral over d beta from minus infinity to plus infinity, e to the, by the way, here I integrate from minus infinity to plus infinity, but you can also change p to ip, and it will be literally the integral like that. That's more convenient form. Beta e minus f of beta. And we have to calculate this integral. Now the key point, the reason why this Boltzmann-Gibbs describes the ergodic distribution we had is very simple. Energy of the system as well as free energy scale like they are proportional to the number of particles. So we have a huge factor here in the exponential. If you, for large number of particles, if you introduce, for instance, epsilon n and f and f, you will get e to the beta n epsilon minus f of beta. And so we are now asking the question how to calculate the integral. How to calculate the integral where exponential is huge. So what can you say about it? What we are supposed to do to evaluate the asymptotic limit as n goes to infinity. Again, I will another mathematical detail. Again, I will not go to much. Suppose you have an integral of this form, and you are interested in the asymptotic limit when lambda goes to infinity. What will be how to evaluate this integral? I can be even more concrete here. Suppose I have x squared plus x to the fourth plus x, whatever, with arbitrary coefficient px. I claim that you can find the limit lambda to infinity in a simple way. What do you think? How to deal with such guys? What is the basic, what will contribute most to this integral? Integral is a sum of terms, roughly speaking. And these terms are of the different order, so you need something most relevant. What do you need to, you want to maximize the contribution? Where the contribution is maximized here?
Around zeros of f.
Not quite. F may be negative. But you are making progress. So actually it's not so much zeros of f as zeros of f prime of x. Why is that? The asymptotic behavior, the leading asymptotic behavior is lambda f of x0, provided that f prime x0 is 0 and f double prime is greater than 0 at this point. There is, of course, also some pre-exponential terms, but we are interested only in the exponential ones. So why is that? What's that? Yeah, it's very simple. You just say that if I have a minimum, then I can expand x naught plus y. I have f of x naught plus f double prime of x naught y squared. And so I get, and the last question is how you have to integrate these things. how it scales with lambda, this integral. This is pre-exponential, which we will not be really interested, but so how it scales with lambda.
Can you do the same thing?
Huh?
Can you pull the same trick? Can you pull the same trick?
Yes. Well, basically, now you simply can rescale y to lambda minus 1/2 y. Lambda disappears from here, but appears from here. So it is lambda to the minus 1/2, and the asymptotic. And in principle, if you extend further, you will get expansion in 1 over lambda. So what I'm basically saying is, it's a very powerful method for treating integral. It's called the saddle point method, or Laplace method in this particular case. There are many variations of this idea in mathematics. That's a very powerful way to find asymptotic values of the integral. And when you have several minima, so you just say trivial thing that at large lambda, it's the minima of f which contribute. It's the minima of f, and the dominant part will come from the deepest minimum, the most minimal value of f will give you the largest contribution to this integral. So generally speaking, the asymptotic behavior is the sum of such exponential corresponding. That's when you have several saddle points. And its generalization is to the complex plane, gives you a lot of more subtleties, but basic idea is this. You can evaluate those integrals. What else I want you to know about it? Well, play around with this. Calculate asymptotic first two terms of asymptotic behavior of this integral. It will contain e to the some power of lambda plus multiplied by some series 1 over lambda to one power, 1 over lambda to another power, and so on. So you can reproduce the whole asymptotic series. Now, returning back to our case, I'm saying this to notice that we now can use this saddle point idea to evaluate the entropy. We reduce evaluation of the entropy from the complicated integral like that to a much more treatable integral from Boltzmann-Gibbs. So we simply now want to know what is e to the, well, we actually just said that this we call e to the minus beta f. F is called free energy because one reproduces thermodynamics. One identifies all these quantities with thermodynamical quantities, and they satisfy the same equation. So all you have to do is to take the minimum of beta, e minus f of beta, and set it to 0. That gives the relation between temperature and beta. So let's see what kind of relation is this. We have, let's do this. We have e minus f, and we differentiate it, plus minus beta df d beta must be 0. And beta is the inverse temperature. It's a very common notation to denote the inverse temperature by the letter beta. It's more convenient in many cases, although temperature is more intuitively. It would be clumsier to discuss weather in terms of beta. Although, well, anyway. So we have the relation then. We have beta determined by this thing, and we have the relation that the entropy is simply beta E minus F, or F is well, sorry. So we have this relation, and it determines entropy in terms of, this determines temperature in terms of energy, and this determines the entropy. And actually, you can easily see that beta is just the product of entropy with respect to energy. That follows from this formula. And we have a more or less normal thermodynamics. All we derive now, we're using this concrete expression, we derive, and I advise you to do this exercise to understand this better, to do all ideal gas, perfect gas with these formulas. But we left so far, I was discussing a rather formal and rather simple things. But now there is a question, there is a non-trivial question which arises. Of course, now with this understanding and understanding a relation of this to the completely integrable system, where you can introduce several betas. Beta is a parameter conjugate to energy, but there are, when you have many integrals, there are other parameters. For example, there is angular momentum is conjugate to angular velocity, and so on. That's all is pretty simple, and with this understanding, I think you will find helpful statistical physics by Landau and Lifshitz, where the problems are discussed from the slightly different point of view. But the only part of this discussion before we go to the really interesting thing, which I wanted to stress, is this relation between delta function distribution, which is sometimes called microcanonical distribution, and the usual Gibbs distribution, which is called canonical. There is in the Landau and Lifshitz you will find also a different derivation of the same thing, not formal mathematical derivation with a saddle point, but a physical derivation when you have a small subsystem of another system and so on. So I recommend you to read the corresponding part of Landau and Lifshitz and compare with what I said. It's two slightly different pictures. But as I said, it's not, all this is not a big deal, at least nowadays. It was a big deal in the time of Boltzmann, but not today. But what is a big deal are properties of the entropy. Entropy is a slightly mysterious quantity. Namely, we know that if you have a phase space and we have a certain domain in the phase space which corresponds to ensemble of the system that moves, but the volume in the px space, the volume is unchanged. At the same time, if we have a system in some initial state, we know that what we call thermodynamical entropy, the entropy grows. That's the second law of thermodynamics. So how to relate these two things? And the answer is quite interesting. The answer is the following. Let's imagine, well, let me first tell you that there's a huge, complicated mathematical investigation of this with different definition of entropies and so on, or what is called dynamical entropy, which depends on time. We will not go into this, but I instead give you some simple intuitive argument how to understand the growth of entropy. Imagine that in our phase space we measure positions of the points of the system with certain accuracy. So we introduce certain error inherent to our apparatus. So roughly speaking, let's imagine that we have cells in the phase space and our device can only tell you in which cell the system is located at a given moment. So we can assume that at the moment 0 we have this picture, the system was located in a certain domain, certain cell of the phase space. What will happen at the moment 1? What can happen is that the system moves, the shape of this phase volume changes, and we will get the picture something like that. And now let's call this is kind of a coarse-graining of the phase space. And let us simply say that the entropy, coarse-grained entropy, is just the logarithm of the number of cells occupied by our system. So if it occupied 10 cells, then it's logarithm of 10, and so on. So here at t equals 0, it occupied 1 cell, and the entropy was 0. What is the entropy? Notice, by the way, that when we have this thing, the volume of the phase space, the volume of this blob and the volume of this blob are the same because of the Liouville theorem. It moves dynamically. So what is the entropy at the moment 1? The coarse-grained entropy at moment 1. It's logarithm of 2. So you see that what begins happening here is very interesting, that while the phase volume, we called the entropy, originally we called the entropy to be a logarithm of the volume in the phase space. And this entropy doesn't change because the volume in the phase space with time is not changing with time. But if you introduce a physical entropy, which is a coarse-graining of the mathematical entropy, because all apparatus have finite precision measurement, so it's just an idealization of this situation. And then it's quite easy to imagine that the entropy will grow, because what eventually will happen is that conditions for that, of course, should be discussed, is that we will get some complicated, very thin, but very long structure at large times. And if we define the entropy as the, so again, it's huge, it can be very, very long tentacles, but it is so thin that the total volume, it becomes thinner and longer each moment. The total volume is the same as the total volume of this blob. So there's no contradiction, of course, with the Liouville theorem. But our device will measure coarse-grained entropy, and it will find that the entropy of this thing is small, while the entropy of this thing is huge. And that's how one explains the growth of entropy with time. The explanation how is basically that it's not exactly the Liouville entropy, so to say, the logarithm of the phase volume, but somewhat coarse-grained thing, and that explains this contradiction.
Excuse me, so what happens to the entropy after Poincare recurrence?
Well, this eventually, here we assumed that we assumed that the system propagates, and the time which we are discussing is much smaller than the recursion time. The recursion time is, for an ideal gas, is something like larger than the age of the universe, or something like that, some huge number, because of the exponentials involved. It's like, roughly, it's exponential of the number of particles, the recurrence time. So there's no question that after, if we go beyond the recurrence time, if we go to this ridiculously large times, then the system will be it will return to the same cell. So there is a periodicity, but, and actually, just to give you, it's quite interesting. It's all, as you see, very subtle things, and it is being discussed up to now. For example, I agreed with some people. Some people are making now new claims about this growth of entropy, that in many systems the ergodicity may not be working, and so on. So even now it is, well, I'll tell you also another thing. There's in the 1950s, there was in Los Alamos Fermi, a great physicist, very good mathematician, Ulam, and Fermi passed, and Ulam, they played with computers. There were first few computers to do computation for atomic bomb, but they decided to do something more peaceful to familiarize themselves, and they did the following. They took a chain, a system with many degrees of freedom, a chain with nonlinear springs, so it's something like potential energy, something to the fourth. And then, so they have a system of harmonic oscillators, and they did the following numerical experiment. So there are many modes, as you see, for harmonic oscillators. They put the initial energy in one mode, but the modes are coupled with each other. And what they expected? They expected ergodicity, that the energy which is put in one mode, will gradually will spread to other modes, and you will have equipartition, or which is equivalent to ergodicity or thermodynamics and so on. Nothing like that happened. In fact, that what they observed was that they put energy in the mode 1, the lowest mode. The energy was gradually transferred to the mode 2, and for a while this mode 2 began to grow. Then mode 2 disappeared, there was mode 3, then finally they returned to mode 1 and so on. So there was a somewhat quasi-periodic process involved instead of this ergodic picture which they expected, and they were very puzzled by the result. And people are still a little puzzled, although there's one of the explanation which is available is that this chain is very close to be completely integrable. But in completely integrable you have quasi-periodic motion. You don't spread over all phase space like we expect in this case of gas. And it's still a question, as I said, people are doing research right now on those things. Quite interesting research, actually. Mathematicians also contributed here. There's the notion of time-dependent entropy was introduced by Kolmogorov. There's the so-called Kolmogorov-Sinai entropy, which is similar to this one, but not identical. It's a little bit more involved and complicated. I actually, for these lectures, I just try to maximally trivialize the construction, not bothering about mathematical rigor. It would be somewhat difficult to derive this, but it's a resolution of the puzzle, actually. It also, I must say that this idea of coarse-graining is also important in quantum mechanics. Actually, people's interesting historical fact that people, when they try first to invent quantum mechanics, they thought that in terms of that it will be just this discrete phase space. Their first attempt at quantum mechanics, basically done by Max Born, before real work, before the work by Heisenberg and so on, was the first idea was just to discretize the phase space and to think that it's quantum mechanics. In fact, it doesn't work, but although the idea is very good and the idea that very natural, that's the first approximation in a sense. But finally, it turns out that it's not that you go to from continuous to discrete numbers here. You go from commuting to non-commuting numbers. So it's much more interesting than that. But in some approximation, you can still think in terms of, in these terms. Okay. As I said, all these things can be explored in numeric and have been explored in numerical experiments, but there's still no good theory for this. Well, let's proceed now. Since we started discussing chains of particles, some chains of oscillators and harmonic oscillators, it's a very natural initial point to go from mechanics and thermodynamics to hydrodynamics. I shall explain. Or more generally to continuous mechanics, when degrees of freedom are continuous, not I mean, not discrete, characterized by discrete number I, but by some continuously varying number. Here I leave, of course, undiscussed huge amount of subtle problems. Of course, not all systems behave like that, and to decide which do, which don't is. We will touch it a little bit later in the course, but still, it's too large, and there are too many explanations. When you have many different theories for the same thing, it means that the subject is not in a very good shape. Okay, so, but hydrodynamics itself is a nice theory and extremely useful. And to go there, let's start from the simple mechanical model. Let us start with a very simple mechanical model. Namely, let's take the Hamiltonian, which is sum plus the model is one-dimensional, and I assume that the X space is a large. I have a large ring, and you have particles on the ring which are flying around. So this is a model. And let's assume that all particles are repelling each other. The first question which we will ask is, what is the equilibrium? Is there some mechanical equilibrium for these particles? Yes. Well, that's clear that we just have this thing. It's a one-dimensional example of which physical system? No, it's a crystal. It's just in 3 dimensions. You will get by the. So we have to solve the. We look at the equilibrium condition. And we find that in the equilibrium we have xk is equal to xk 0 at equilibrium is equal to k multiplied by a, where a is the distance, so it's just L divided by the number of particles. There is a small puzzle here. So we have to, the small puzzle here is that it seems that you have, how shall I put it? You have many equations. You have for each k, you have one equation, and you have only one arbitrary parameter here. Let's check. So let's check how it is resolved. Such things should always be of some concern, that we have too many equations for practically no parameters. But actually, what's happening is we have v prime. I will better put absolute value here. V prime of k minus L a. And I have sum over L, and it should be actually, and this should be 0. So you actually need to satisfy all these equations, but it is, as a matter of fact, it's just one equation, because when you always can shift L to L plus A, to L plus K. So far it's just the normal mechanical equilibrium. Now let's look at the slightly non-equilibrium position. We write it down as xk0 plus yk. And then we will get the Hamiltonian, which is, I shall replace p by velocity, have yk square plus sum of we have linear term plus non-linear term, 1/2 k minus L, yk minus yl square, plus higher terms. Now, plus etc. Now, this guy give you 0, the first term, why? We have here k and l summation up.
The two terms cancel when you switch k.
Yeah, roughly speaking, this term is symmetric when you interchange k and l. This term is anti-symmetric. And also that was another check that we are in the equilibrium. Linear term in the equilibrium should not be there. And it is not there indeed. It's just because of this feature we see that. But we can now rewrite the Hamiltonian, the energy, or Lagrangian for that matter. There's no difference here. Plus 1/2. And here I will have the following. I shall change variables. Let me see if I'm doing this right. Yeah. So we have harmonic oscillators. And let's determine what kind of excitations exist, what kind of motions exist in this system. Well, there are many interesting features here. So once again, how I obtain this this thing? I obtain it by expanding near its quadratic expansion near the equilibrium, and that is so we have oscillators like that, related by this. But there are also there is also interaction between this and this and so on. It's not necessarily the interaction. And now I'm going to make a crucial approximation, which is it probably will be better for me to have the Lagrangian. The approximation which I want to make, further approximation, is to consider this motion as continuous, and that will lead us to hydrodynamics. This crystal what kind of motions would you expect in this chain? We have a chain of particles. What do you think? How it will? Suppose you push it somewhere, then what will happen? Well, you see, if you push one, it will transfer the force to the other, and so on and so on. So it will move, then stop, because it lost its energy. It passed energy to this next one, to the next one, to the next one. How shall we call this phenomenon when you have propagating energy? It's a wave, yeah, it's a wave. And moreover, as we will see, it's basically a sound wave. But let me, and now what I'm going to do is to show that it's indeed a sound wave and to calculate the speed of sound in this chain. For that, the most convenient thing is to replace yn of t by continuous function n of t. Of course, it's an approximation. We must understood what when it is valid. So, and I'm asking now a very general question. Under what conditions it's legitimate to change discrete index by continuous index, by a continuous coordinate? So what kind of condition we should, when, for example, when we have a finite difference like that, for example, when it is correct to replace it by a derivative? How would you answer to this? It's very intuitive thing. You just have to be sure that when n changes, yn don't jump, that the changes is small enough, right? So give me a precise mathematical criterion which we expect. Or we can actually argue, we can either so we have dy dn plus, if we keep expanding it further, so one form of the condition is simply that this term is small, that this is much larger than this. So if dy dn much larger than the... you can also say a very simple condition, even more intuitive condition than this, namely, for the process to look continuous, we need this quantity not to be large. So what would you suggest here? It's much smaller than what? It's much smaller actually than yn itself. You see, that's the good condition, which tells you that the value of y changes from side to side, but it changes very little, very slowly. So when this is, and we will check it explicitly, that then in this case you can. you can actually replace sums by the integrals, differences by derivatives, and so on. And if we use it, if we assume that this is true, we will approximate the Lagrange function as following. It will be 1/2 y dot square of n and t minus, here we have something interesting, c square y square dy dn square, where c square, what I'm doing here is I'm simply expanding this thing in terms of the derivative. So maybe you will tell c will turn out to be the speed of sound. So what is the speed of sound in terms of the potential of the crystal? You can figure it out by looking at this expression.
Just v double prime ending.
Just what?
V double prime of ending.
Well, remember we expanded it in n here. So we actually will have sum over n, v double prime 1/2, v double prime of na multiplied by n square. Now the last question, since we're running out of time, we will play with this model next time, of course. But just what is the role? What will happen? This c square will turn out to be speed of sound. Now suppose that we have not a repulsion between these guys. But suppose we change the interaction term so that it is now attraction. What happens physically and mathematically in this case if you go from repulsive atoms which form the crystal to attractive atoms? Both what happens with the formulas and what happens with the real crystal.
So studying heat goes down the range goes from being a stable equilibrium to an unstable equilibrium?
Yes, it is unstable equilibrium. What happens mathematically?
Second derivative switches sign.
Actually, what happens if it changes sign, so the speed of sound will be imaginary. Imaginary speed of sound, as speed of sound enters, it comes, I'm running slightly ahead of myself, but it's okay, I think. Speed of sound, you know that sound wave is some sine or cosine of certain expression. When you put imaginary value inside this sine and cosine, they blow up, they become hyperbolic sine and cosine. And that we will see next time. This also means that the equilibrium, there is equilibrium even with repulsion, because with attraction, because you have, it's terribly unstable. And we will see instability will be our point of interest also later. Okay, let's stop here.